Welcome AP to the beginning of Chapter 19, Chemical Thermodynamics. This is part 2 to Chapter 5. So we need to remember what we did in Chapter 5, plus some of these other topics we've already covered. So in Chapter 14, kinetics, okay, remember kinetics tells us how fast the reaction goes. So it talks about speed of reaction. Okay, so in chapter 14.5, we talked about activation energy, okay, which we call it capital EA, or sometimes you may see AE. We had these activation graphs where you had to figure out how fast a reaction went. And so the EA was that energy needed to make the reaction occur. So when you had very large activation energy, that means it was very slow, very slow reaction. So we want very low EA, so that way that it has a faster reaction. So when you saw those activation energy graphs, we want little tiny. Now whether it's endo or exo, that's a completely different story. But with chapter 14, that told us how fast a reaction goes. And then with chapter 15, equilibrium, it depends on how fast a reaction goes. So this is when you can have like adding a catalyst to make the reaction faster. We talked about intermediates, stuff like that. So we have a lot of knowledge. So like I said, part 1 of thermal was chapter 5. And we're going to get into some of that review right here, but we need to get going. So we have two very important words, spontaneous, but AP prefers to hear thermodynamically favored. This is a good thing, okay? It basically tells us that a reaction can occur on its own. So with chemical thermodynamics, it's concerned with energy relationships and chemical reaction. It helps us understand why a reaction favors going one way over another. So why does a reaction prefer to go A to B versus B to C, B to A? Okay, why does it prefer to go this way versus the other way? Okay, or if you'd like to think of it instead of, if I kept A and B as the reactants, I'll do it that way. Why does it not go in the reverse? So remember, we call this the forward direction, and then the other way is the reverse. And then when we put them together, we got obviously equilibrium. So why is one direction more favored than the other? Well, let's get some good review of chapter 5. Okay, in chapter 5, we talked about enthalpy. Enthalpy is also another way of saying heat. Transferred from the system to the surrounding. As long as we have constant pressure, we got to have that constant pressure, so then we can do the coffee cup lab, calorimetry. Okay, so with the coffee cup lab, that's when we were trying to figure out how much heat was transferred from system to surroundings by using obviously the coffee cups, measuring the temperature before and after, and so forth. So we have enthalpy, we have equals delta E, which is internal energy, as you see right here, internal energy. We have Q, which is heat, and then we have W as the work being done on the system or by the system. So we have P delta V, and that P right there is what makes it constant pressure, because you don't have a triangle next to that P. But remember, we also know that P delta V is also negative W. So if we substitute everything in, we have first law of thermodynamics, delta E, Q plus W. We know P delta V is negative W, so remember those W's cancel. So that enthalpy depends on heat. But we have to know if the heat's going into the system or is it coming out of the system still. So in relations to that, we need to talk about processes that happen on its own. So we call this spontaneous. That's how we've always known it, but it makes more sense, as in AP prefers to hear thermodynamically favored. And you're going to hear, how do we know if it's thermodynamically favored? Is it like endo versus exo? Is it like a high delta H or a low delta H? Like, what is the criteria to make it happen on its own? So we call this outside intervention. Means you did nothing. You actually just put the reaction out there and it happened on its own. So let me give you like some examples. Say you took 2 eggs and you dropped them. That's thermodynamically favored. The eggs dropped when they hit the surface. Now, where students kind of go a little overboard with this, they'll be like, well, you put them in your hand and you dropped them. Yeah, that's a little too explicit there. You're going way too detailed there. The point is, you dropped eggs. Will the eggs break on their own? And yes, it's going to break on its own. The reverse reaction, taking the 2 eggs, leaping back into your hands and going back into the shell, well, that's not thermodynamically favored, as it will not occur on its own. Rusty nails, because iron surrounded by oxygen, you're going to produce something called iron oxide. Okay, going to happen. Iron always rusts. Okay, gas is expanding. This one's a big one. Okay, because this is going to lead us into this next topic about particle movement, which we have a very fancy word for that, like I said, coming in 19.2. Say right here you have gas A and you have gas B, okay? You open the valve. So when you open the valve, what have we learned back from chapter 10 is that all gases will mix homogeneously. We don't have to do anything. They're going to mix on its own. So right here, if you had part A, it says evacuated. So that means you have no gas here, but you have actually 1 atm of gas. So if you have gases in here, and then as soon as you open the valve, the gases will mix on their own. You didn't have to do anything. Now, let's go back. Yes, you opened the valve, but did you have to stir it? Did you have to tilt the flask on one side to the other? Okay, kind of like a teeter-totter. No, those gases traveled from one side and then was traveling back and then traveling back. It's spontaneous. As soon as you open the valve, it will mix on its own. But will the gases go back to the one side? No, they won't do that. So that's why, and I'm going to put this over here, when you, open the valve, the gases will mix on its own, but they won't go back into the original container, It doesn't work like that. So how do we know if something is thermodynamically favored? Exothermic reactions, We want those delta H's or that Q at constant pressure, we want negative. And why? Because it's easier to lose heat than to gain. So we also know that exothermic reactions, they will happen at their own rate. So if they go fast or slow, they're going to do it whatever speed that they want, but as long as it's exothermic. There is a but to this, Thermodynamically favored are exothermic reactions. However, there is one time melting ice is thermodynamically favored, but it's endothermic. Let's take a little sneak peek what I mean by that, So you have your ice. Ice freezes less than 0 degrees Celsius. If I put it on a counter, I got my table here. I got it on my counter, which my counter is at room temperature, aka 25 degrees Celsius. I just put a piece of ice out there. Will this melt on its own? Yes, because the heat is coming into the system. The ice is the system. The heat is coming in and it's melting the ice, but because the heat is coming in, that's endothermic. But it will happen on its own. I didn't have to do nothing. I just put a piece of ice on a counter and it's going to melt. You've all seen this before. You put ice in your cup of water. It's going to melt on its own because why? The water is hotter than the ice, It's still thermodynamically favored, but this is one exception where it's actually endo, but also thermodynamically favored, So how is equilibrium brought into this, So we call it reversible equilibrium, and then you have irreversible, which means goes to completion. Back in chapter 3, when we talked about like limiting reagents, where we had A makes B, that's it. It's done. Game's over. Okay? So with thermodynamically favored reactions, they do have a direction. They do prefer one direction. So let's go through both of them. So reversible reactions, aka equilibrium. In one direction, the reaction can go back and forth between states, but along the same path. And what they mean by the same path, that they're talking about like endo versus exo. So reversible process can restore the system to its original state. So if you have A makes B, and you start with 1 ATM, and you start the reaction, you're going to restore it back to its original condition. The path taken to the original is exactly the same path as the reverse. So back in chapter 14, when we talked about like K forward versus K reverse, it's going to be the same rate. Okay, they both went on the same path. There is no net change, which means your delta E is 0. So if your delta E is 0, and we know delta E is Q plus W, that means they're the same value, but opposite signs. Okay, so one's just positive, the other one's negative. Okay, there's no net change between the system or the surrounding when the cycle is complete. Completely reversible reactions, they're very, very slow. Okay, very, very slow to maintain, which means you have an EA that's going to be very high. Okay, consider the intervention, the inner convention, the inner conversion of ice and water at 1 ATM, and we call this normal melting point. Okay, it could also be normal boiling point too, as long as it's at 1 ATM. 0 degrees Celsius, okay, which means you have ice, but you have ice and water at equilibrium. Okay, so back in the day, called chapter 11, okay, those phase graphs. Okay, when you are at 0 degrees Celsius, you are at equilibrium. You have water as a solid and you have water as a liquid. You have both of them at the same time if it's at that temperature and at that pressure. Okay, so now let's say we put a piece of ice on the table, as I just did my beautiful diagram above, but we have it on the table at room temperature. We add heat to the system from the surrounding, but we didn't have to do anything because it automatically transferred the heat. It was thermodynamically favored because the surroundings, aka the room temperature, the surroundings were warmer than the ice, which the ice was the system. Okay, so with our piece of ice, we already know that the heat came in to the system. So we can melt a mole of ice to form a mole of water. It's thermodynamically favored at room temperature. And actually, it's thermodynamically favored at any temperature, but it has to be above 0 degrees Celsius. Notice I didn't say at 0 degrees Celsius. It has to just be any number above 0. Okay? But if I want to return it to its original state, if I want to reverse it, it's going to be not thermodynamically favored at room temperature. Okay, so what do I mean by that? All right, so here we go. We have table, and we have our puddle of liquid water. If I keep the surroundings at 25 degrees Celsius, it will not happen on its own. And why? Because you need the temperature of water to be less than 0 to get it back to ice. So can I restore it? No, I can't. Okay, I cannot take this and make ice. Okay, ain't gonna happen if it's still 25 degrees Celsius, okay? We need to remove the same amount of heat from the system and the surroundings. So notice right here, I have a Erlenmeyer flask, and it says that, I'm reading right here, spontaneity can depend on temperature. It definitely depends on temperature. At temperature higher than 0, ice melts spontaneously to form liquid water. So as long as that temperature is above 0, it will happen on its own. But spontaneous reactions, remember we call this AKA thermodynamically favored, okay? If I take this liquid water at temperatures less than 0, the reverse process, the water freezes to ice, is spontaneous. So if I make this temperature less than 0, then it will go back to ice, okay? But if above 0, then it won't be thermodynamically favored, okay? And then at 0 degrees, the two systems are at equilibrium. You don't have water yet, but you don't have ice. You have them both at the same time. So this is why thermodynamics, they have an actual direction. We have to know what temperature is, and we have to know what's going to happen. An irreversible reaction, well, basically means not equilibrium. So the process cannot be reversed to restore the system and surrounding back to its original state. And how do we know this? Well, a great example is that hot water always flows to cold. It cannot be reversed. You can't make that cold water go back to hot unless you add heat, okay? So we can't make the cold, we'll just say cold water, go back to hot water spontaneously, aka thermodynamically favored, because we have to apply heat. And that means you had to interfere. And if you interfered, okay, you intervened, that means it's not thermodynamically favored, okay? So a different path with different Q and different W must be taken, okay? So this is why it's very important to know what type of reaction is. So remember, a process that's thermodynamically favored in one direction is not thermodynamically favored in the opposite direction unless temperature changes, okay? So a process that's thermodynamically favored in one direction and not in the other, we're talking about at the same temperature, okay? But if temperature changes, then it can be thermodynamically favored if you try to restore it, okay? So we have to pay close attention to temperature, okay? All right, we're going to talk about these particle movements on this next video.